Okay, similarity and dissimilarity measures. Similarity measure means how do we see that? Okay, not shared. Okay, now it is visible, right?
Yes, sir.
Now we discuss about the similarity and dissimilarity measures. How much two objects are similar, how much they differ, those things are important in some algorithms like clustering, those things. So similarity measure, numerical measure of how alike two data objects are, is higher when objects are more alike. If they are same, then they are more similar, then value of similarity will be very high. Often falls in the range of 0, 1. So usually when they are measuring similarity, they measure with the scale 0 to 1. So 1 means they are almost same, they are same. 0 means they are completely different. So any value between that is something like 0.2 means 20% nature of those two objects is same, something like that we can understand. Opposite to similarity measure is the dissimilarity measure, numerical measure of how different two data objects are. If more value, then more dissimilar. Less value, less similar. Less value, less dissimilar. Lower when objects are more alike. Minimum dissimilarity is often 0. Upper limit varies. Most of the time, similarity is nothing but 1 minus dissimilarity, or dissimilarity is 1 minus similarity. These two are conjugate type of things. So then third thing is proximity refers to a similarity or dissimilarity. So people may measure two objects, whether how much they differ by using one of these, similarity measure or dissimilarity measure. They can be convertible most of the times. Similarity, dissimilarity for simple attributes. The following table shows the similarity and dissimilarity between two objects X and Y with respect to a single simple attribute. So attribute type, nominal. Nominal, we can say only whether they differ or not, right? Then similarity will become either 0 or 1. There is nothing like it's 50% they are same, 20% they are same, 70% they differ. So for nominal, it is easy. So if they are same, then similarity will be 1. If they are not same, similarity will be 0. So vice versa, dissimilarity. If they are same, dissimilarity is 1. No, if they are same, dissimilarity is 0. If they are not same, dissimilarity is 1. So ordinal is used something, a formula here, d equal to mod of x minus y by n minus 1. So values map to integer 0 to n minus 1 when n is the number of values. S equal to 1 minus d. We need to see this, let's say, in an example later. Then we will understand what is this x and y. X and y are two objects. Then what is the mod value between them? If they are ordinal, something like small, big, then there is no meaning of big minus small, how much value you get. So that is the problem here. Then we'll see examples, how do we do this. Then interval ratios, it is easy to compute. So they are intervals. We know that what is difference between those two. So get the just difference, then you'll get dissimilarity. Then similarity may be s equal to minus d or 1 minus d, whatever that. S equal to 1 by 1 plus d. All these things you can take. S equal to e power minus d. S equal to 1 minus d minus min of d, max d minus minimum of d. Scaling this is again. So you need to go through all these things again from the textbook. You will get more examples there to understand these things. So we need to understand there are different similarity, dissimilarity measures. For different algorithms, we may need to use different these measures. That's why we need to have, we need to understand all these measures. So one measure, similarity, is Euclidean distance. All of you know that in geometry you might have used this. Euclidean distance, if 2 points are given, x, y, then dxy is square root of k is equal to 1 to n, xk minus yk whole square. So these are points in space. when n is the number of dimensions and xk and yk are respectively the kth attributes or data objects x and y. I think you remember that if points are given x1, y1 and x2, y2, what is the Euclidean distance between them? Square root of x2 minus x1 whole square plus y2 minus y1 whole square. That is the formula which you have studied. Same thing here, Euclidean distance. Standardization is necessary if scales differ. Then to get the Euclidean distance, if scales differ, then we need to standardize that attribute because different attributes may have different scales. Then one attribute will have larger values, other attribute will have smaller values. So you make standardization of each attribute, then get the Euclidean distance. That is what I'm saying. If dimension y is very high number, something like y is the weight, x is the height. Height, if measured in meters, it comes like 1.2, 1.3. And weight measured in kilograms, it comes like 60, 70, 80. Then always the second one is dominating. The first one is see whether it changes 1.2, 1.3. The change will not be considered as a much impacting on the distance. So only the second variable contribute more to the distance. That's why we need to normalize both, bring them to the same scale, something like 0, 1, standard scale or whatever that it's, you use. Then get this Euclidean distance. As I told you, Euclidean distance is different points on the space, then get the Euclidean distance by the formula. And you can see example here, use that formula, you'll get these values. Then another thing is the Minkowski distance. The difference is here. Earlier we were taking, instead of mod square, then we are taking first mod value, then summation of r rth power of each mod value, then take 1 by r because you are increasing power r, then again you need to get the root of r. So this is Minkowski distance, r is the parameter here. So where r is a parameter, n is the number of dimensions, and xk and yk are respectively the kth attributes or data objects x and y. This is similar to your Euclidean. Here, you can still write mod of this. Mod also will give you the same value. Mod xk minus yk whole square. Square root is nothing but 1 by 2. Instead of 2, they are writing r. R inside, 1 by r outside. That is called Minkowski distance. Minkowski distance examples. R equal to 1, city block, Manhattan, taxi cab, L1 norm distance. So we have seen it's in regularization, we are using L1 norm, then that is one of the Minkowski type of thing. Even Euclidean is also R equal to 2. It is more generalized Minkowski. R equal to 2 will give you Euclidean distance, R equal to 1 will give you L1 norm. R tends to infinity, supremum. L max or norm, L infinity norm is also called distance. This is the maximum difference between any component of the vectors. So you have x1, y1, x2, y2, x1, y1, x1, x2, x3. If there are n dimensions xn, whichever dimension you have maximum difference, that is called supremum. That is also called infinite Minkowski distance with r equal to infinity. Do not confuse r with n. That is, all these distances are defined for all numbers of dimensions. N is the dimension of the data. R is the Minkowski parameter. These two things you should differentiate. So R can be 1 to infinite, but n is fixed number if your data set has n attributes. Then there are some examples you can go through this, how by using this formula, if you compute for different R's, you'll get this distance matrix. Another thing is the Mahalanobis distance. Is a famous statistician from India, Mahalanobis. Mahalanobis xy, the distance is defined like this. It is defined for vectors. So x minus y transpose sigma inverse x minus y whole power minus 0.5. That means 1 by this will come. Sigma is the covariance matrix. Whoever can recall your statistics, then you can find covariance matrix between two objects. Once you find the covariance object, then represent them as vectors, then take X minus Y transpose sigma inverse X minus. All these are available packages, but you should understand that it's a Mahalanobis distance, what is its formula, those things, when to use those things. But actually you don't compute these things, but you should know that what will be the parameters to find out the Mahalanobis distance. So two vectors should be given, then it should find out the covariant sigma matrix. Then this whole formula will give you Mahalanobis distance. For red points, the Euclidean distance is 14.7. Mahalanobis distance is 6. So if you see here, the Euclidean distance is very high, but Mahalanobis distance is not high because it's in one dimension, they vary much. But in Y dimension, they don't vary that much. So in Y dimension, if you see, it is at 3 and it is at -3. Only 6 difference is there. So you are getting 6 difference as Mahalanobis distance. Whereas in X dimension, it has something like -7 to 7. So it is almost 14.7. So in whatever dimension it is having the less distance, that will come in Mahalanobis. In supremum, whatever the distance you have maximum in any dimension, that will come as a supremum. So Mahalanobis distance example is given here. Matrix, two vectors are given 0.3, 0.2, 0.2. Two vectors 0.5, 0.5, B is 0, 1, C equal to 1.5, 1.5. Then Mahalanobis AB is 5. Between these two, the distance between A and B, it is 5. Between A and C, it is 4. When we look in the space, A and C looks like very far, A and B close. That is Euclidean distance. But when it comes to the Mahalanobis distance, in one dimension, it is very close in Y dimension. Even here also it is close between B and here. So, but when you find the variance, this sigma matrix, you are getting Mahalanobis distance is different from the Euclidean. You should remember these distances we will use in different algorithms. So what distance will make us clustering good in hierarchical clustering, that distance we need to take. Common properties of a distance. You can also define your own distance, but they should follow these properties. Distances such as the Euclidean distance have some well-known properties. dxy, any distance between any two is always positive or 0. That is 0 only if the point is same. Then it is symmetric. The distance between x and y and x is same. It is also satisfies triangle inequality, means if you get distance between x and z, the distance reaching from x to z through any other point should be more than this direct distance. Then it is called triangle inequality. dxz less than or equal to dxy plus dyz. D is the distance function, where dxy is the distance between points x and y. A distance that satisfies these properties is a metric. So if a distance satisfies that, that is a metric. Similarity between binary vectors. Common situation is that objects x and y have only binary attributes. Like asymmetry attribute will have only binary, right? Either the object is there or not, whether that attribute is present or not in that object. So common situation is that objects x and y have only binary attribute. Compute similarities using the following quantities. F01 means the number of attributes where x was 0 and y was 1. Then F10, the number of attributes where x was 1 and y was 0. Then F00, both are zeros. F11, both are ones. Simple matching and Jaccard coefficients people will use. SM, simple matching coefficient. This is number of matches by number of attributes. So F11 means both have these values. F00 means both not have these values. It means same values for both attributes, both objects. The number of attributes having same values is nothing but F11 plus F00. Then total number of attributes is this. That will give you Jaccard similarity. This is very important, this Jaccard similarity for document matrices or document similarity, we'll use this Jaccard similarity. Number of 11 matches by number of 0 attributes. J is means 1-1 matches means only the items which are common, that is important. Don't eliminate the which are not common. Don't go by which are not common. Go by only which are common. Then remove which are not common in numerator and denominator also. Then that becomes a Jacob coefficient. So SMC versus Jacob example. Then if you see here X and Y, what is the simple matching coefficient here? We need to see that in how many places these two vectors or these two objects have same values, right? Count here how many you have here. This is not 1, 2, 3, 4, 5, 6, 7. So 7 places they have same values for both X and Y, and remaining places they don't have. So how many total? 3, 3, 6, 10. So 7 by 10. So you are getting 0.7. So Jacob similarity is F11. F11 is here 0 because no column is 1, 1 in this. That's why Jacob similarity is 0, but simple matching coefficient is 0.7. So these two are same if you consider SMC, but if you consider J, they are not same at all, let's say. So that is the difference between Jacob similarity and simple matching coefficient. Then another way of finding similarity for documents is cosine similarity, the angle how much they make. So if D1, D2 are two document vectors, then cosine of D1, D2 equal to D1, D2, the inner product of D1, D2. In other words, dot product by norm D1 by norm D2, where D1, D2 indicates inner product or vector dot product of vectors D1 and D2, and norm D is the length of vector D. So example D1, D2, and then if you remember your dot product formula, 3 into 1 plus 2 into 0 plus 0 into 0, like that, then you'll get cosine distance between D1, D2 is 0.3150. This is nothing but how much of angle they make. Correlation measures the linear relationship between objects. Statistical measures are there. If two vectors are given, then we can find out correlation of X and Y. That is defined as covariance of XY. Then standard deviation of X multiplied by standard deviation of Y will come in the denominator. Those also represented as SXY, SX, SY. Then there are formulas how to compute this SX, SY, and SXY. Formulas are given, and how to compute the means X bar, Y bar. Formulas are given here. Once you compute, you can compute the correlation of XY. Then visually evaluating correlation. Scatter plot showing the similarity from -1 to 1. So here what happens, as X increases, Y is decreasing, completely opposite. That is the extreme case. The last one, if you see, as X increases, Y also increases in the same ratio. Then it is called positive correlation. So correlation value is always between -1 to 1. You can see here it's saying how much they vary with respect to one another. If one is increasing, other one is also increasing, and with the same ratio, then correlation will become 1. If one is increasing but other one decreasing, but not in the same ratio as decreasing or increasing, then your value changes between -1 to 1 here. So drawback of correlation is what here. So you are getting, it's a zero correlation between them, but there is correlation between X and Y. We have seen it's up to some extent whenever X is increasing, Y is decreasing. After that, X is increasing, Y is decreasing. If you make this graph two parts, then you can see there is correlation between X and Y. As X increases, Y decreases. But second part, as X increases, Y also increases. So if you see as the two parts, then there is correlation. If you don't see as a two parts, simply by computing the formula, you are getting 0. This is one problem with the correlation. So there is actually correlation, but this 0 is the differentiating term. Before 0, the correlation is different. After 0, the correlation between X and Y is different. So correlation versus cosine versus Euclidean distance, when to use. Compare the three proximity measures according to their behavior under variable transformation. Scaling, multiplication by a value. Translation, adding a constant. So if you scale the values, then correlations, will it change? Cosine distance, will it change? Euclidean distance, will it change? That is what we are looking. If you translate from one, let's say adding some constant to the existing values, how do they change? Then if you see invariant to scaling, cosine, if you change the scaling, cosine distance will not change, correlation will not change, but Euclidean distance will change. Similarly, if you do translation or addition, cosine will change, correlation will not change, Euclidean distance will not change. So correlations, whether you do scale the values, whether you translate the values, your correlation will be same on which data set, before and after. So that is the advantage of the correlation. Then they have given some example, finding all three measures, and they are showing that correlation is having all the same values, let's say, after translation, after scaling also. Choice of the right proximity measure depends on the domain. What is the correct choice of proximity measure for the following situations? So which measure we need to take, that depends on the which problem we are working. Comparing documents using the frequencies of words, documents are considered similar if the word frequencies are similar. Comparing the temperature in Celsius of two locations are considered similar if the temperatures are similar in magnitude. Comparing two time series of temperature measures in Celsius, the time series are considered similar if their shape is similar. That is, they vary in the same way over time, achieving minimums and maximums at similar times, etc. So you need to see that, let's see how temperatures rise and how temperatures come down. If that graph is same, then we'll say those two are same. Comparison of proximity measures, domain of application, where do we apply these proximity measures? Similarity measures tend to be specific to the type of attribute and data. Record data, images, graphs, sequences, 3D protein structure, etc. tend to have different measures. So same measure will not apply to all types of data. However, one can talk about various properties that you would like a proximity measure to have. Symmetry is a common one. So if you get a distance between x and y, then y and x distance should be the same. Tolerance to noise and outliers is another. How much if tolerance means if two outliers comes, will your measure, whatever you are computing, will that change drastically? Then if that doesn't change drastically, it is called tolerance. Ability to find more types of patterns. So can you find, by using that particular measure, more patterns in the data? Many others possible. So when we take the different domains, different problems, then we'll get idea what proximity measure will give us good algorithm. The measure must be applicable to the data and produce results that agree with the domain knowledge. So whatever measure we take, that should give good results. And that result, whatever we are getting, that also should be consistent with the knowledge what we have in that domain. Then another types of measures, information-based measures. Information theory is a well-developed and fundamental disciple with broad applications. Some similarity measures are based on information theory. Mutual information, various versions. This is called, this we use in decision trees, entropy, all those things. So this information-based measures are also important. Mutual information in various versions, maximal information coefficient and related measures, general and can handle nonlinear relationships, can be complicated and time intensive to compute. So these measures are complex, they take more time to compute these things. But these can also handle nonlinear relationships, not only just linear distances, nonlinear distances also, these can find. Information relates to possible outcomes of an event. Transmission of a message, flip of a coin, or measurement of a piece of data. All these things will come here. The more certain an outcome, the less information that it contains, and vice versa. So if it is more certain, means there is not much information. The less information that it contains, and vice versa. So for example, if a coin has two heads, then an outcome of heads provides no information. Because always you will find head, right? It is not bringing any new information. So more quantitatively, the information is related to the probability of an outcome. The smaller the probability of an outcome, the more information it provides, and vice versa. So here, small probability, more. If one probability is almost 1, then there is no information. Entropy is the commonly used measure for information. So there are formulas to find out entropy based on probabilities for a variable event x with n possible values, x1, x2, xn. Each outcome having probability p1, p2, pn, the entropy of x, hx is given by hx equal to -1, I is equal to 1 to n, pi log 2 pi. This again, you can use packages to find out entropy given on these. Even to compute entropies, you need to provide probabilities of each outcome. Then what are the possible values? Like if you take tossing a coin, there are two possibilities. X1 will become head, X2 will become tail. Then what is probability of X1? Head 0.5, then P1 will become 0.5. Tail probability is 0.5 means P2 will become 0.5. If you take dice, then there are 6 possibilities, x1, x2, xx, then each probability will come 1 by 6 if it is an unbiased dice. Then once you get x1, x2, xn values, p1, p2, pn values, you can simply compute entropy by using this formula. Entropy is between 0 and log 2n and is measured in bits. This entropy is a measure of how many bits it takes to represent an observation of x on average. Because it's log 2n, right? It is measured. So it always gives you in bits wise 0, 1, 0, then 0, 1, 0, 1, 1, 1, like that. So entropy examples, some examples are given here. For p equal to 0.5, q equal to 0.5, for fair coin h equal to 1, then your entropy is equal to 1. Then for p equal to 1 or q equal to 1, h equal to 0. So it is certain that always you will get only head if head probability is 1. What is the entropy of a fair four-sided die that you need to find out? So for that you need to do 4 values four-sided die, right? So 4 values x1, x2, x3, x4. If it is unbiased, take 1 by 4, 1 by 4, 1 by 4, 1 by 4. Then use your entropy formula. This, then compute, then you'll get answer for this. What is the entropy of a fair four-sided die? Entropy for sample data. So some other data set is taken here, then count, then probabilities, then minus p log p, then you can compute the entropy there. Entropy for sample data, whatever we have taken there, then use this formula, compute that. Here probabilities are coming by mi by m. The outcome, how many times that mi appeared, then our total number of outcomes is m, something like that. Then mutual information is other entropy measure or information measure. Information one variable provides about another. Formally, ixy equal to hx plus hy minus hxy. So first we need to find out entropy, then find out hx, hy, then remove the minus hxy, where hxy is the joint entropy of x and y. Then hxy equal to minus of I sigma j minus pij log 2 pij. Then there is formula is given how to find out joint entropy for 2 variables. Then mutual information of xy is given as hx plus hy minus hxy. For discrete variables, this is easy to compute. If it is a continuous, then the sigmas will be replaced with intervals. Maximum mutual information for discrete variable is log 2 minimum of nx and y, where nx and y is the number of variables xy. Then another measure is maximal information coefficient. Applies mutual information to 2 continuous variables. Then consider the possible bindings of the variables into discrete categories. Then nx multiplied by ny less than or equal to n power 0.6, where nx is the number of values of x, ny is the number of values of y, n is the number of samples. Then compute the mutual information normalized by log 2 minimum of nx and y. Take the highest value we need to take here. This is called maximal information coefficient. All these things you need to spend by looking at the textbook. You need to solve them on your own, then only it will go into your mind. General approach for combining similarities. Sometimes attributes are of many different types, but an overall similarity is needed. For the kth attribute, compute a similarity skxy in the range 0, 1. Define an indicator variable delta k for the kth attribute as follows. Delta k equal to 0 if the kth attribute is an asymmetric attribute and both objects have a value of 0, or if one of the objects has a missing value for the kth attribute. Then delta k equal to 1 otherwise. Then similarity xy means for each attribute level we are finding the similarity. Delta k equal to 0 or delta k equal to 1. Then we are counting that, let's see how many attributes are similar by the total number of attributes. This same formula which we have seen is converted into a mathematical thing here. Then you can also use the weights. For some attributes, if you want to give more weight, you can multiply with that attribute similarity with WKs. Then can also define a weighted form of distance. Then this xk minus yk is the distance between two same attribute. Then take Minkowski. In the Minkowski distances, you are putting weights multiplication.